Question number 16, if you see, that's from the potentiometer. So that's a very probable zone when it comes to examination. There's a potentiometer wire PQ of length 1 meter. And of course, this is the driver cell. There is another cell having an EMF of 1.02 volt that has been given. And there is connected through a resistance. There is a switch. With this switch open, now you need to see the null position is obtained at a distance of 49 centimeter from Q. That means from this side, that's going to be 51 centimeter. And we need to calculate the potential gradient. Have a look at the question. The option says the potential gradient has to be written in terms of volt per centimeter. Now say, at the null point, current through galvanometer would be 0. So therefore, potential difference through this resistor would also be 0. So it means the entire potential difference will be 1.02 and even 1.02 here. So rest is quite a simple thing. The potential difference between PJ is 1.02 volt and downstairs is 51 centimeter. So option number 3, 0.02 volt per centimeter is the potential gradient, potential per unit length. All right, let's see question number 17. Question number 17, that's from rotational motion. There are two uniform circular disks. They are rotating independently and they are coaxial as well. And the parameters are given. The moment of inertia first, I'll call it as I1. The moment of inertia of second, that's given, I'll call it as I2. This is omega 1, this is omega 2. So let's do in terms of variable. Now it says, at some instant they got stuck together and started rotating as a single system. So we need to calculate the kinetic energy of the combined system. Let's try to do a very known format question, and that would be requiring the idea of conservation of angular momentum. Let me quickly show you how the figure goes. So to show something like this, this is the first disk, this is the second disk. They got stuck together and eventually friction will force them to rotate with a common angular velocity. But the torque due to friction net becomes 0, so angular momentum is conserved. So what will the expression be? I1 omega 1 plus I2 omega 2 will be equals to I1 plus of I2 multiplied by omega. It's simply angular momentum conservation. And then we are supposed to calculate the final kinetic energy. So that's going to be half I1 plus of I2 multiplied by omega square. No difficulty at all in calculation. That will give us option number 1 as the correct. All right, let's go to question number 18. Question number 18, electrostatics. Now what does it say? The charge capital Q is distributed over two concentric conducting thin spherical shells. So total charge capital Q has to be divided. And the condition is there, the surface charge density, they are equal. Then in that given case, we also need to compute the electric potential at the center. So let's do, the first thing is that if I generate the equation, let's say Q1 is the charge in the inner, Q2 is the charge on the outer. That's a first. Also, Q1 by R square will be equals to Q2 by capital R square, all because of the reason the surface charge density, they are equal. And if I solve these equations, I will be getting the value of Q1 as capital Q into R square by R square plus capital R square. Likewise, Q2 would be Q into R square by R square plus capital R square. So it has to be split into two phases. First, calculating the charge, and now calculating the potential at the center. So the value of potential will be K, where K would be replaced by 1 by 4 pi epsilon naught into Q1 by R plus K Q2 by capital R. Using the expression, potential due to a sphere inside will be KQ by its own radius. So that's the net potential. You need to plug the value of Q1, Q2. When you do that, you would get option number 1 as the correct one. Let's go for 19th question.